Hello everyone. Today we will continue our last question paper where we left on question number 8. Now we will going to discuss question number 9. Now question number 9. Here it is asked about data quality dimensions. Right. Now we have three data quality dimensions: inaccuracy, completeness, and consistency. See, inaccuracy, see, for example, like we will discuss with examples, a student intended to rate a faculty number 5, like excellent, the best out of 5, that 5 out of 5, but accidentally typed 1, or student gave an 5 on overall rating, but 1 on clarity of instruction, or somewhere he mistakenly did a wrong thing. Now, this is inaccuracy. We fix it by automated validation checks. This is a program that flags the data immediately, saying, "Hey, these two scores don't match up. Is the right?" Kind of like checks backwards. Now, completeness is missing data. For example, a student skipped a question 3 on the survey. Now we have a blank cell, right? Fix this, we cannot go further if the student doesn't click that checkbox or answer that particular question, then we won't be able to go forward. That is completeness. And consistency, it has different scales. Like the chemistry department uses a rating scale of 1 to 5, but history department uses a scale of 1 to 10. Now if we combine these two doesn't actually add up. Like one is 1 to 5, one the other is 1 to 7, 1 to 8. So like these are obviously the points where consistency matters. Now completeness, we can fix it with mean mode and increasing incentive of for response. And then there is consistency. We can fix consistency by using standardized instruments and map scales. Now we will go to question number 10, handling missing data. Now, handling missing data, how can we handle missing data? So there are two approaches: basic approach and simple advanced approach. So in simple approach, we delete the entire row. Like we can delete the entire row uh, to ignore the tuple, right? Imagine a survey of 100 people. If 20 people skip from one question, deleting all 20 rows might make your final sample size too small and therefore biased. Right, we only do this if the missing data is very rare. And global constant, now global constant, we fill every blank with a single word like unknown. This is easy, but it pollutes your data, right, with too many of the same values. Now if we do this with unknown or neutral, it will pollute the data, which will make it difficult somehow. And now we will go to the advanced imputation, which is mean median mode, that is the central tendency. This is a common, right? We fill the blank with average score, points to the center tendency. This keeps the overall average correct. And the other is prediction. Use a regression or decision tree to predict the value based on the other attribute. Most accurate, it is the most accurate one. uh, this is where we get smart, right? We use the students other 20 answers to predict what the missing 21st answer should have been. This is done using models like regression or decision tree, and it's generally the most accurate, preserving and subtle relationship with the data. Now we know the all four methods how we can handle the missing data. Basic approaches: ignore the tuple, global constant, advanced Imputation is mean, median, mode, and prediction. Now let's go to the next question. Question number 11, outliers and smoothing. So next we look for the data. This is acting abnormal, what we call outliers. See, if the average in the class, our class is 22, and one student is 65 marks, like, yeah, then the person is an outlier. Yes, the person is an outlier. Now, how do we find them mathematically? We find them mathematically like by Z score, IQR method, red visualization. So, what is Z score? This calculation, this calculates how many steps a value is away from an average. If the person's score is more than 3 steps away, it's flagged. Right? Value is more than 3, then it's flagged. IQR method, interquartile range. This is visually best seen on a box plot. Right? The other one like the visualization, box plot, and scatter plot. So any point that sits too far outside the main box and whiskers of the data is considered an outlier. Now, once we find the noisy data, we use data smoothing to reduce that noise. Think of smoothing like ironing a shirt, right? Now, binning, point to the binning bullet. We group nearby sources into bins. Then we replace all the individual scores in that bin with bin's average. That makes the data much cleaner. Now, other data smoothing method is regression. We draw a smooth mathematical line that best fits all the data points, and we use that line to represent the trend, ignoring the tiny variations. Fit the data into a function, right? Now, that is our smoothings. We can use either binning or regression. Now, question number 13, normalization techniques. Now, the normalization is a vital because it makes features with widely different ranges comparable. Think of it as an converting currency. We need a formula to standardize the value. So we have three main techniques. First one is min max. Point to the min max formula, right? The min max scale data to fixed range. Now this is the easiest to understand. We find the absolute minimum and maximum in the data set, and we transform every value uh, so it fits perfectly between 0 and 1, right? Now Z score. Z scores and standardization. It is standardization. This is the most common for analysis. We transform the data so that the new average mean is 0. The new standard deviation is 1. A Z score of +2 means a value is 2 standard deviation above the mean. Right. Now these are the formulas written here. And the third one is decimal scaling. Now, what is decimal scaling? Uh, this is just moving the decimal point, often used for a very large numbers. We divide the value by 10, where is chosen, j is chosen, power of 10 is chosen, so the biggest number becomes less than 1. So we divide v by 10 to the power j. It might not be visible because of the screen, but it is 10 to the power j, and j is how we decide how much value of j is, that v will become less than 1. Now we have discussed the three normalization techniques as asked in the question. Now we will go to the question number 14, the next question. Now let's uh, apply this formula to our faculty workload hours dates. Right. Now data set uh, Here, notice the massive range from 35 hours to 1600 hours. That is really big. Mean maximum is really high and minimum is really low. So the min max we set 35 to 0.000 and 1600 to 1.000. All the numbers are now squished perfectly between 0 and 1. Now Z score, this gives us a much more meaningful result than the average is 593, and the 600 score is basically 0. Now the 1600 score is plus 1.866, 1.866, right? Z score, and it is nearly two standard deviations above the average. The 35 score is minus 1.034. It is one step below the average. Z score shows the relative position of each number more clearly than the min max scale. Now, this is how we find out the values discussed in the above before the before slide. These are the formulas that how we calculated the values, right? And we can next slide, that is Z score normalization. How did we calculate it? The formula, then computed mean, computed standard deviation. These were our scores, right? Decimal scaling normalization. Then we applied the formula, and after applying the formula, we put in the values. Right here, like as we discussed before, the decimal scale normalization, we divide the J, right? J is 4 here because the max is 1000. So now we have to divide it by 10 to the power 4 to make it less than 10, less than 1. Now question number 15, right? Normalize the values using 13 values using the methods in question number 13, right? Now we will normalize it. So we will use the min max normalization, Z score normalization. In the question 13, the data set that was given. So we will have to apply that on apply these normalizations on that data set. And here we put the values and we got 0.075 as the answer, and for B, that is how we put the formula, then we substituted the values, and that is how we got the answer 1.7. Wait a minute. Right, so the formula that we used for min max normalization is x is equals to my x minus x min upon x max minus x min, right? Here it is written the same formula, if you can see, right? uh, can, this is the formula, and this is the formula, right? And then the Z score normalization is the formula, that is Z minus u upon my a, that is sigma, right? This is the formula. Now we substitute the values and we get the Z score. right? Now decimal scale normalization is right, the value that is x divided by j to the power 10 to the power j, and j is 50, right? In the question it is 13, and to that to the 13 we will divide it by 100, so we will get 0.13. Now comparing min max versus z score is first, we can say characteristics which are of min max normalization: scales value into fixed range, usually 101, preserves relative distance, simple to compute, right? So what are the pros? Resolves all relationship exactly, bounds data strictly, example neural networks, right? Works well for bounded data, required for neural networks, keep all the data on the same scale, and the disadvantage is highly sensitive to outliers. One extreme value compresses all other data. Now, Z score. Z score, here it is, like it's very robust against the outliers, essential for algorithms. Assuming Gaussian distribution, right? Mean becomes 0, standard deviations become 1, no fixed output range, handles outlier better, works for Gaussian distribution, as I said before, requires for PCA clustering SVM methods. And the con is does not produce a fixed bound range, harder to interpret values, range is not limited. So these were the differences between min max z score. Now, which is more appropriate when we use min max, when we need data strictly between 0 and 1, data has no extreme values, algorithm needs bounded input neural networks, and when we use z score is data set contains an outlier, data is normally distributed, you want the standard statistical analysis. So Z-score is a more appropriate in real-world datasets because it is robust to outliers and distribution aware. But min-max normalization is preferred only when strict bound values are required. Now we will go to question number 17. What is question number 17? It's Pearson's correlation. Now, what is asked in the question is computing correlation, state whether relationship is positive, negative, and interpret the value. Now, this here is asked that we take the data from question number 4. So, we have taken the data, the age and productivity, and we will put everything in the in the formula, right? The formula that is given to us, it is x1 minus x2, some summation, right? That is not n, that is summation, that is summation, that is in the formula here, it is not n. uh, this is not n, how can this, this is not n, and we will put it in the formula, and after performing all the calculations, right, like the basic calculations, we will get the result is equals to 0.659. Now interpretation are the correlation value is positive, strong positive correlation. As age increases, productivity tends to decrease, right? And tends to increase. Did I say increase? I think I said decrease. Tends to increase, right? And the nature of correlation is 0.8 to 1 strong positive, 0.4 to 7 moderate positive, 0 no relation, -4 to -0.7 negative, -0.8 to 1 -1 strong negative. Since R is 0.62 659, it is moderate and strongly positive correlation. And Pearson correlation coefficient between age and productivity is 0.659, which indicates a moderate strong positive relationship correlation, which means that as age increases, productivity also tends to increase. The variable are positively strongly related. Now we'll go to question number 18. Right. Binning method. Right. What is binning? Binning is a, how can I explain how we will be explaining it is, binning is a data smoothing technique used to reduce noise in data by grouping values into bins, right? Intervals, we can say intervals. Instead of using raw data, raw values, we analyze the group data. This binning technique is used in data processing, outlier handling, noise reduction, feature discretization, right? Discretization. And there are two types of binning, that is equal width partitioning and equal frequency partitioning. Now, what is equal width partitioning binning? That is, we divide the range into an intervals of equal range, equal size. Right, the data is divided into n bins of equal sizes, and the formula for it is x max minus x min upon n. Now, for example that we have taken here, the width is 52.5, and how we will divide it is, we will divide it by range 215 minus 5, that is 210, and the compute bin width. Now we will divide, like the we will divide 215 by 5, and that will give us 52.5 the width. Now bin created the intervals. So bin 1 is 5 to 57.5, 8 items. 57, bin 2 is 57.5 to 110, that is 2 items. Bin 3 is 110 to 162.5, there are 0 items in that. And bin 4 162.5 to 215, that is 2 items here. And now we will see the equal frequency partitioning. Each bin contains same number of data points. Data divides data, so each bin has same count. So now we have total items as 12, and we will create 4 bins, so we should have like 3 items per bin. And what will we do? We will create a bin 1 which has 5 10 11, bin 2 13 15 35, and bin 3 50 55 and 72, bin 4 92 1204 and 215. Now what are the differences between these two is, first, when we talk about interval sizes, equal width has same interval sizes, while equal frequency, the interval size varies, while data count is unequal in equal width, and that is equal in equal frequency. Outlier handling of equal width is poor, while outlier handling for equal frequency is better than equal width. Distribution for equal width is sensitive to skew, while equal frequency it is balanced. Now, equal width binning divides a data set. Like if we talk about what will be a final answer, we can say that equal width binning divides the data set into fixed size intervals, while equal frequency binning ensures each group has same number of values. Equal frequency handles skewed data better, while equal width is simpler to implement. Now we will do the next part of the question paper, that is question 19. Question 19, we have symmetric binning attributes and nominal gender. So students, gender, skills, and skill 3, skill 4. Now there are two ways we can do is Jacquard dissimilarity and Euclidean's distance. First is focuses on present skills, and second one is standard geometric distance. So when we put values of the pairs in the formulas, we get pair AB, pair AC, pair BC, and like how. So we have a tie. A pair could pair B, A could pair B, or A could pair with C, right? And this is where we use our secondary non-mathematical attribute gender, right? There were two males and one females. So AB have different genders, male, female, while AC share the same gender, male, male, right? This is after we put the values in the formulas and we get these answers. Then we will go to the next slide, uh, which is how we figure out which will be the best pair. So while the gender don't dictate collaboration success in analytics, while mathematical metrics are tied, we use other factors to break the tie, assuming similarity in the background or demographic factors might contribute to easier communication. Now, final recommendation is we choose student A and C as the most compatible pair because they are equally skilled but they share the same gender, offering us potential boost in the team compatibility. Worst is BC, and purely based on skills, right? We, as I said, it is written also that skill distance AB and AC are tied. However, introducing gender as a compatibility factor, AC share the same gender high skill similarity, while AB have different gender high skill similarity. BC are the worst match of all friends. So we can say that student A and C are the most compatible pair for collaboration. uh, Thank you. This concedes our session on data processing and collaborative analytics, and we have finally discussed all our 19 questions from the question paper. My name is JALAJ Mehta. My roll number is IC2K2344, and I'm from MCA 5th SEM, Section A, IIPS DAVV. Thank you, image sources.